Hello everyone, let us continue our discussion. So we are in week 8 and this is our lecture 2. And if you recall, in the previous lecture we derived the stress distribution, shear stress distribution over a cross section. And in fact we considered rectangular cross section and I section, and for them we derived how the shear stress varies over the cross section, right? And if you recall, tau, that is the shear stress at a particular level, and we derived the expression is VQ by IB, right? So that's the expression of shear stress distribution over a cross section. Now let us take an example. So example 1. So we have a cantilever beam. The length of the beam is 2 meters and the beam is subjected to an UDL. The intensity of the UDL is 10 kilonewton per meter. Now, for this beam, we have rectangular cross section. And the dimension is 50 millimeter by 75 millimeter. Our task is to draw the shear stress distribution, and for that we consider the end A of the beam AB where the shear force will be maximum. So for that, let us quickly draw the shear force and bending moment diagram. Now, reaction at the end RA, and we also have a moment here which is MA. Now RA is equal to 10 kilonewton per meter over a length of 2 meters, so it is 20 kilonewton. Similarly, we can find out MA, which is 10 times 2, that is the total load, and the lever arm in this case is 1 meter because we have the length of the beam as 2 meters. So 1, so again it is 20 kilonewton meter. Now, let us draw the shear force diagram, and for that again, we take a section at a distance x from the end B. So Vx, that is the shear force at x, is equal to 10, that is the intensity of the UDL, times the load x, so it is 10x. That means at x equal to 0, that is the free end, shear force is 0, and when we have x equal to 2 meters, that is the fixed end, we have shear force as 20. And it linearly varies. So if we draw a straight line, and this is positive, right? So this is 20. Similarly, mx is equal to 10 times x is the total load times x by 2 is the lever arm. So 10x square by 2, that is 5x square. Again at x equal to 0, the bending moment is 0. And then at x equal to 2, that means at the fixed end, we have 20, right? And it varies as shown. So this is hogging moment, so it is negative. So 20 again at the end, and the variation here is quadratic variation. It's the equation of a parabola. So now we have the shear force and bending moment. Bending moment will offer bending stress, that also we have solved earlier. Now shear force is V is equal to 20 kilo Newton. Now tau is again VQ by IB, so our task is to find out Q, and we know the shear stress at the top and at the bottom is 0, so at the middle we have to find out. So over the neutral axis, Q is A times Y bar. So what is A? We have 50 times 75 by 2 into 75 by 4. So for the section above neutral axis, we have CG somewhere here at the middle, and that is 1/4 of the total depth from the neutral axis, right? Okay. So if you solve this, you get Q as 35156.25 millimeter cube. Okay. So what is I? I is 1 by 12 B, which is 50, times D cube, that is 75 cube. Now this is in millimeter to the power 4. So if you convert that into meter to the power 4, you get 1.75 into 10 to the power minus 6 meter to the power 4. So this is in millimeter to the power 4. Okay. Now tau at the neutral axis, we have 20 kilonewton. So 20 into 10 to the power 3, that is in Newton, into we have Q 35156.25, that is in millimeter cube. So if we convert that to meter cube, we'll have 10 to the power minus 9 divided by I, which is 1.75 into 10 to the power minus 6 into the width. B, width is 50 millimeters. So this is, so width is 50. That means 50 divided by 1000. Okay. So we can cancel these quantities, and then we are left with 20 into 35156.25 into 1000 divided by 1.75 into 50. So if you solve this expression, you get 8.04 into 10 to the power 6 Newton per meter square. Or in other words, the shear stress is 8.04 NPa. Now if you draw the variation, so it will start from 0, it will go to the maximum value, and which is symmetric, and this value is 8.04, right, which is in MPa. So that's the shear stress distribution for this beam at the end A, where we have the support. And because this is a cantilever beam, we have the maximum value of the shear force there, and that will produce maximum value of the shear stress at the neutral axis level. So if we design this beam against this shear stress distribution. So we have to actually design based on this value 8.04 MPa. Right? Okay. So this example shows how you can derive the expression for shear stress and its distribution over the cross section. Let us take a different example. In this problem, we have a simply supported beam and a point load at the middle, and the point load is 10 kilonewton, and the length of the beam is 3 meters. The beam is made of steel. Young's modulus is 210 GPa. That means 210 into 10 to the power 9 Newton per meter square. And it is made of ISMB 175. I'll explain the meaning of this in a minute. But before that, let us first solve the bending moment and shear force for this beam. Again, for this problem, we are worried of shear stress distribution, but let us solve the complete problem. You can also solve for the bending stress, and then you need the material. Here the material is steel and its Young's modulus is given, right? So as the beam is simply supported, we have reactions at the two ends. So RA and RB. Now RA is 5 kilonewton because it's a simply supported beam and with a point load at the middle. So the reactions will be half of the load applied. 10 kilonewton is the load. So reactions are 5 kilonewton, 5 kilonewton. Now if we draw the shear force diagram, all of you know how to draw the shear force diagram. So we consider left up, right down is positive. So this is 5 kilonewton. So this is our shear force diagram. Similarly, we can also draw the bending moment diagram, and it has a sagging bending moment, so it is positive at the middle as per our nomenclature, and this value is 5 kilonewton times 3 by 2, that is 1.5, so it is equal to 7.5 kilonewton meter. So we have our BMD also ready. Now the section is made of ISMB 175. Now this is a very standard section. Actually, for all steel sections, we have a handbook. This is used in steel design. So this handbook, it gives these kind of detailed table, and here you can see the properties of different IS sections are given. Now out of that, we have used ISMB 175, that means it is here. And if you look at the section type, it is a I section, right? I section diagram is given along with the dimensions. So the depth of the section is H. You can read this H here. So ISMB 75 means 75 millimeter is the depth of the section. Similarly, we have B, that is the width of the flange, then TF, thickness of the flange, TW, thickness of the web, and also the moment of inertia about xx, yy, and the radius of gyrations. All these sectional properties are given and their proper units are also given here. So from this table, you get the detailed property of the ISMB 175 section. So what we'll do, we'll read this line, and from this line, we'll get all the properties of the section that is required. Otherwise, we need to evaluate the moment of inertia, cross-sectional property, and all other, say, the Q that we are going to find out today. For that, again, we have to split this because this is an I section. If you recall, in the previous class, we derived the expression for I section, and there you have the expression in terms of TF, TW, and capital D, small d, right? If you recall, all these dimensional properties we used, but we don't need to actually refer to those calculations because we don't need to start from the beginning and evaluate the sectional properties, which is given here. Now coming back to the problem, for this ISMB 175, the moment of inertia about xx axis is given and it is 1272 centimeter to the power 4. So what we get, 1272 into 10 to the power minus 8 meter to the power. And the depth of the section is 175 millimeter, that means 0.175. Now, the maximum bending moment is 7.5 kilonewton meter. So, let us quickly find out the bending stress and then we'll come back to the shear stress distribution. So, if for bending stress, you know, sigma by y is equal to m by I. So, sigma is equal to m by I. So, m in our case is 7.5 kilonewton meter. So, we have to convert it into Newton meter, that means 10 to the power 3 times y, which is 0.175 by 2 divided by I 1272 into 10 to the power minus 8. And if you solve this, you get 51.59 into 10 to the power 6 Newton per meter square. So effectively we have 51.59 megapascal. Bending stress you can draw. It has a sagging profile. So we have tension at the bottom and compression at the top, and accordingly you can draw the bending stress distribution. The maximum bending stress is 51.59 MPa. Okay. Now let us solve the shear stress distribution, and for that again this is a I section if you recall, and for I section we have to first find out for the flange and then we will come back to the wing. Now for the flange we have the cross sections given. Again from the same table we can get the cross section. The width is 90 millimeter. Thickness of the flange is 8.6 millimeter. Thickness of the web is 5.5 millimeter. And the total depth is 175 millimeter. So the depth of the web, if you calculate, it is 157.8. Again for this symmetric section about the neutral axis, we have to find out Ixx, which is also given for this cross section, that is here. Now here just I want to mention one thing. If you go back to the table, normally these I sections come with this curvature. You can see here we have a curvature here and also a curvature there, where the flange joins with the web. But in our case, we will not consider for the time being this curvatures, and we will consider them to be straight, as you can see in this cross section. Okay. So for flange, our task is to find out Q, and that is not difficult because we have to consider this flange portion only. So the area is 90 times 8.6 times 157.8 divided by 2 plus 8.6 divided by 2. Now, all these dimensions are in millimeter. So if you solve this, you get 64396.8 millimeter cube. At the flange level, now we can calculate tau f, which is VQ by IB. Our V is 5 kilonewton, so we have 5000 Newton times Q, which is 64396.8 into 10 to the power minus 9 divided by, we have I 1272 into 10 to the power minus 8 times B, which is 90. So it is 0.0. Now if you solve this, you get 0.28 into 10 to the power 6 Newton per meter. So that means 0.28 MP. If you recall, shear stress at the extreme fiber is 0, and now we have the shear stress at the bottom of the flange. So we'll solve the remaining part in a minute, but before that, let us just mark the cross section and the stress that we have just derived for the flange part, right? So what we have a rectangular cross section and neutral axis is at the middle. So at the top we have 0. Similarly at the bottom we also have 0, and then we have at the base of the flange, this is 0.28 MP. It is symmetric, obviously we'll have the same value here also. So this is 0.28 MP. Now let us focus on the web part only. So for web part, again we have to consider complete flange and then part of the web as we move from the neutral axis, right? Okay. Now Q for the web part is again we have to come somewhere here. So we consider the additional part inside the web. And let us first consider the moment when we just come to the point here. At that point, we can easily derive the expression, because earlier, if you recall, it is tau equal to VQ by IB. Now, V, Q and I will remain same when we are at this point, but we are just at the wave part. The only thing is, in place of B, which was earlier the width, that is 90 millimeter, now we have to consider the width of the wave, and which is 5.5 millimeter. So we can easily find out the expression for tau. For that, what we have to do, 0.28 multiply that with B. So we had 0.09 and then divide it by the new B, which is the thickness of the wave, 5.5 divided by 1000. So the value of tau is 4.58 MP. So now at this level we get the value. So this is 4.58, and now we have to calculate the value of shear stress at the neutral axis. So for that, again, we have to consider the complete flange and then half of the wave, right? Okay. So now we consider half of the wave, and then again Q will change this time. So what we have is the expression that we derived in the previous class. We can also directly use that. So let me just go back to the previous class note. If you recall, here is the expression. So you can see the expression of Q is here when we consider the full wave part up to this point. Okay, so we consider half of the wave, and then for y equal to 0, if you put in this expression, we will get the Q. And we also have the expression for this tau when y equal to 0, right? Y equal to 0 is the neutral axis. So we can directly use this expression today, or otherwise you can also find out Q and then apply the formula VQ by IB. So we will use this expression and we will find out what is the shear stress at the neutral axis. Okay. So let us now find out directly using the expression instead of Q. So tau Na, if you put in that expression, our shear force is 5000 times we have (90) as the width of the flange, 90 by 8 times capital D square, so that is 175 square minus small d square, 157.8 square, plus TW 5.5 divided by 2 into, divided by 8 into 157.8 square. And this is again in millimeter cube. So we have to multiply that with 10 to the power minus 9. That we'll do in a minute. So VQ divided by I 1272 into 10 to the power minus 8 times we have B, which is 0.0055, and we also have 10 to the power 9, right? So that's the expression for tau. So what we have done, we use the expression directly, what we derived in the previous lecture, and then now we solve the shear stress value. And if you solve this, you get 6.4 MPa. And if you recall, the variation is again quadratic, so it will be a quadratic variation. And so this value here is 6.4. Here it is 4.58. Okay. So now you can see how we use the steel table to design a section when we take actual problems. And as you progress in the course, in third year, you will learn steel design. There you'll use these steel tables very frequently, and you'll get all the sectional properties directly from the steel table. Now, before we close today's lecture, I just want to draw your attention that if you look at this shear force and bending moment diagram, so at any say arbitrary section here, you can see the section experiences both bending stress arising from this bending moment as well as shear stress coming from this value of the shear force. Now at the middle, when we have maximum value of the bending moment, there we have the maximum value of sigma that we have already derived for this problem. But there at this point, if you go to the left of this point, we have full value of the shear, and on the right part also we have the full value of the shear force. Then for any other sections, we have both of them are acting over the cross section. And if you recall the failure theories, we also combine these different stresses to find out the overall stress level, and we can also design the section using the combined effect of shear and bending. That is not the purpose of this lecture, so we will not go into the details, but just to mention here that in actual design problem, you have a particular section, both shear and bending, and in fact, there may be other stresses also. For example, torsional stresses are also maybe there. So you have to make a combination, and then finally you have to get the combined effect before you design the section. But the theory starts from what we discussed today. So if you talk about shear stress distribution, you get the shear stress distribution here for this I section. So let us close here. As we progress, we will see how we can consider an arbitrary section, and for an arbitrary section also we can develop the shear stress distribution for that section. That we'll take in the next lecture. So with that, let us close here. Thank you very much.